Read it. She wants the one of. All the ones. She wants all the ones in Amos.
Okay, let's get through No. No. The next chapter is super duper important. So you're pretty much into the rest of the semester. It's a special set of equations coming from nuclear. You might have to think just what they might be. The next chapter, chapter 4, is a very special set of equations you're going to use in the semester. Do you have any idea what they might be?
What kind of equations?
Special.
Special equations. A, B, C, D, E, F. Does it have numbers? Does it have letters? I got word. A number?
I should just start using
Do they have the Greek alphabet?
No. S's, Y's, T's.
Pervert equations. Pervert equations.
What?
Oh,
no. Who's class? That was your guys' class. Who was it? I think it was Jada.
What?
No. We're doing the gas law, and I wrote E equals MRT on the slide. What are you looking up? Who's the pervert? Okay. I write the ideal gas law, you just look up the That is not what it says.
Equation. Carbon is a whore. Carbon is a whore.
Well, dots with everything, yes.
And how to build water bottle tower.
Yeah.
No. How to build water
Yeah,
bottle
we're finishing up relative velocity.
The structure wasn't very sturdy.
Yeah, but we worked so hard on that, someone collapsed it.
I don't know.
I thought we just all ended up having.
Why are we drawing a different page? Were we all turned around at 12:05 or 12?
In person.
Yeah, I think it was.
What lab is it?
That's why she left, I'll run her off.
Yeah, we ran her away. Scared her away.
So, let's kind of look at this idea of person standing on the ground, person in the train car, okay? So, we will. Hold on. Let's say the train car moving with a velocity. Velocity of the train relative to the ground. Okay, the person inside the car starts walking. I'm going to give you the velocity of the person relative to the train car. Now, how do we look at? We say what is the velocity of the person relative to the ground. What do you think? Up to the person standing outside the train or not?
Don't you just add them?
Yeah. So velocity of the person relative to the ground is the sum of the person's velocity inside the train car plus velocity of the train relative to the ground. So this is the basic concept of how relative velocity works. Again, imagine someone's in the train car tossing a ball up and down. They only see the ball moving up and down. If you're standing outside the train, you see the ball moving in arc. You know, so okay.
Wait, go up. Wait, when you go
Right.
If you're not getting hand cramps, you're not riding fast enough.
I feel. Feels so
It's so much.
I'm trying really
Actually,
hard.
I don't have any, like, usually I have something, but that right there, not in my repertoire stack.
You think
Just
I did this, I have one. Sorry. Did I know you? He's gonna be like, calm. He's gonna come back next week.
No, I'm just gonna be like, you're gonna be.
My hands slipping. I started reading it, and then I tried to read it.
Okay, so
Miss it.
let's say a person is trying to cross a river in a boat, okay? The current of the river is flowing, the person aims straight across the river. If they aim straight across, and so let's go ahead and draw the river.
To calm down.
So we have the velocity of the water relative to the shore.
65 pounds, that's pretty damn good. All the upper weights, yeah.
The person gets in a boat, they're trying to go across the river. They aim straight across.
That was my one plan.
Is that velocity WS?
It's impressive.
Yeah. Velocity of the water relative to the shoreline. This is going to be the person's velocity, or the velocity of the boat relative to the water.
No.
But how does the boat actually travel? At a dynamic, you know, sorry, I forgot to take that. So of course, this is going to be the velocity of the boat relative to the shoreline. So again, according to the person in the boat in the water, they're going straight across, but the shoreline sees you going across and down at the same time. Okay, so what can we say? We say, well, the velocity of the boat relative to the shore is going to equal the velocity of the water relative to the shore plus the velocity of the boat relative to the water. Now, we have a couple you already know. I'm going to call that the positive y direction. So the problem tells you the velocity of the water relative to the shore is going to be a negative 0.61 meters per second J hat. On the X. The velocity of the boat relative to the water. .16 meters per second I hat. So then we want to figure out what that velocity of the boat relative to the shore is. So this is one of the easiest vector additions you've ever had. So we know that this is going to be the x components. And the y components. And when we put our numbers in, the water to the shore is 0 in the x direction. And the velocity of the water to the shore is negative 0.61 meters per second in the y direction. In the y direction for the boat. And so you end up with And then from there, was okay, so from there you could do the you can figure out the angle that it's at. You use your inverse tangent. You find that that theta is going to be 27.7 degrees. And then see how long would it take to cross the river and how far downstream would it be carried. Okay, so the river is 250 meters across. And which component is going to be responsible for the boat crossing the river? The X component. So I can say, well, 250 meters, the X component, yep, 1.16 meters per second, and I get 216 seconds to cross the river. What about how far downstream? Which component is going to dictate that? The Y component. Now, what can we use to figure out the Y component? Not quite. What's your definition of velocity?
It's like displacement over time.
And so the magnitude of that is going to be 0.61 meters per second. The time to cross is 216 seconds. So you get carried 132 meters downstream. So again, relative velocity is not going to end up on assignments. It's not going to end up on exams. If you are someone taking the MCAT, this will show up. Maybe now's the time for everyone to switch to veterinary. No?
I just don't.
Yeah.
She's hard.
You're gonna do a lot of videos. Okay. Everyone have this. All right, motion with constant acceleration. Which one is that?
That's crazy.
I know, we just have to cover that constant.
So this stuff.
Why is it 17 slides?
I think that.
Because that's still
stuff.
Oh, actually?
Yeah.
I would think for this one.
So,
Next exam. Yeah, that's fine.
motion along the line when the net force is constant. You can see the various graphs here. You see that the position over time is going to be an exponential increase with a constant acceleration. Your velocity will be a linear increase in velocity with a constant acceleration.
This is not on the test, right?
No.
Okay.
Now,
No, it's not.
and then your acceleration versus time graph, you're always good for a constant, like for a constant acceleration, your acceleration versus time graph is always going to be a linear line at a certain number. It'd be the same thing if you had like a constant velocity. Your velocity versus time graph would also be a linear line at a certain number. You know, it's just
I literally get so scared coming here, low key.
I don't, I just think in my head, how can I make?
okay. Those of you who had me in chemistry, you've seen that little guy before.
Yay.
What is this? What does that mean when that shows up?
It's like really important.
Okay, so these next couple of things we're going to be talking about, these are probably they may be the most important things you do this semester. And since everybody knew what they're called, These are called the kinematic equations of motion. I'm gonna tell your dad.
That's fine.
I
I thought you were telling me, I was like, you don't know my dad.
So the whole point is we're going to be analyzing motion. As you see here, we have it set up for one direction. You'll find these kinematic equations are identical for multiple directions. So you can analyze 1 or 2 dimensions. You could analyze 3 dimensions, but in 100 level physics, we just don't get there. Okay, so let's think about where this might come from. So if I have, what's the definition of acceleration? Right, it's the rate of change of velocity. Okay, so that means we can turn our delta V into A delta T. Then we can break this into components. The delta T is going to be a constant, so it can be inside. And so as you see, we can actually break this into the individual components. So you can have delta Vx is Ax delta T. Delta Vy is Ay delta T. And we can analyze the dimensions independently. So then as you notice here, your kinematic equation breaks down into V final minus V initial equals the acceleration times time. So that's your kinematic number 1. Anytime you're solving a problem, you hope this is the one you can use. Most of the time it's not. Okay. Here's our second kinematic. Now, where do you think the 1/2 comes from? That's one. I have a final velocity and initial velocity. It's 2 velocities. That's the average of the 2 velocities. So your average is your so that's your average. So then if we say, well, what's the definition of velocity? Let's just work with the averages. So velocity is what over what? Right, so we're going to have delta x over delta t. Then that's our average velocity. So then that the average becomes 1/2. So this will be your second kinematic equation. How many of these do you think you're going to have?
8. 4.
4.
You're so smart.
Okay, so this one here is one that you'll use quite a bit to solve problems. So if we remember, our first kinematic equation So then what we're gonna do is we're going to take our second kinematic equation, right there. Okay, well, let's solve this one for B final. So we're going to take that and substitute in for B final. So then inside the parentheses, we're going to get 2, the initial x, oh, sorry, there should be a plus sign in there. Okay, now we can multiply these in one at a time. If I multiply in the 1/2, then I'll multiply in the delta t, end up at now this one here can also be your friend sometimes, because a lot of times you're going to have you have systems where your initial velocity is 0, so that entire first term disappears. Now, sometimes we have problems where we don't have any concept of how long the system was being measured for, so we end up with the fourth kinematic equation. Well, again, we have our first kinematic equation. This time we'll solve for acceleration. We're going to use that. No, I solved for the wrong. Solve for time. We're going to use that with the second kinematic equation.
Is it plus or minus?
We're at.
Oh, never mind, never mind, you put, that's a different.
Well, then, only people remember factoring.
Beyond my years.
Go all the way across.
First, outside, inside, last.
Foil.
Wait.
First, that's.
Good, man.
So you have that. So let's see, the factor that those top two, you're going to end up with B final squared. You see, then you have the final times the initial plus the final the initial minus the initial squared. So you have the acceleration. You see these two middle terms cancel each other. So you end up with And then from there, you can solve for the kinematic equation. So the whole point of coming up with multiples of these, because sometimes there's information you don't have. So you need to have multiple ways to solve a system. These 4 equations should do that for you.
It's all coming back.
Now, this was how you actually derive these kinematics, but what we have is a slide that just has all 4 of them together, which you can use as a reference. And Pingu is wise. Listen to Pingu's advice. Apparently, and I'm betting I'm the only person who knew that Pingu.
I knew it was a pain.
Oh, did you?
I watched it
Yeah, new dude.
religiously as a kid.
Yeah, new dude.
The hell's that thing?
I never watched it. It was on Netflix when I was younger.
What is
That's not Perry.
this? What is this?
And
It's a
penguin.
penguin.
Perry is a platypus.
Yeah,
That is a penguin. That is a penguin.
Perry's a different species.
What is this? From
Penguin.
what?
From
Penguin.
Pingu. New dude.
Penguin.
He got his own dang show.
It's just like Caillou, but non-verbal in a big way.
This guy has his
And it
own
was made out of
show.
like clay.
I didn't know that.
Yeah, it's like claymation.
It's simply a bit over like everything.
Yeah.
He gets mad a lot.
He was like the penguin version of Caillou.
Yeah.
Oh, that's fair.
I remember the soup episode.
Okay, so let's try to use these.
Why are we doing multiples?
So this would be a Dr. Bruss question.
Oh, that's crazy. From the parent moss plant.
So you have these, have any of you ever heard of sphagnum moss? You ever heard of that?
Like,
Yeah.
I've never heard of that. What is it?
It's
Wow.
it's
It's
like
like
a
a
really specialized moss that grows in bog that makes like a sheet.
Yeah.
Wow. Well, when it fires out its spores, those spores can undergo an acceleration of 360,000 meters per second squared. Now,
Yes, they do.
it's just like, apparently moss gives birth much more violently than humans do.
It's like a rendering of what happened. They actually make popping noises when they
Do they?
burst. Yeah.
Wow. Well, they're just trying to describe your spores as far as.
I don't know. I don't.
There's actually a couple plants that do it that way.
I think rust.
Really?
Spurge is one of them, and little explosions that send the seeds.
I think someone baited him into it.
I mean.
I always like the little seeds that fall off trees are like half a helicopter. So assuming constant acceleration of this magnitude, how far will the moss spore travel in 0.4 milliseconds starting from rest? Okay. So the first thing you notice is that your acceleration can I do a calculation with those two numbers?
Yeah.
Yes.
You can use.
Yes.
Your first equation.
What was one of the first things I taught you to do? Make the units what? Make them map.
Yeah,
You have issues.
I would do that.
Make a match. You cannot do seconds and milliseconds.
Well, in my defense, I didn't see that.
So. Remember, your millisecond is in the third second, so we'll just go 0.40
That was all.
in the third second. Now, we use them together. Just make sure you pay attention to your units. If they don't match, you gotta make them match.
Why didn't you do a train track?
Yes, the answer to that
Well, I
question
could have,
is.
but one of the easiest things to do is know your conversion number. Then just take the number you have and put on that extension. Because then if I actually calculated this, it'd be like 4.0 times 10 to the negative second seconds. But I can just leave it the way it is and slap on the 10 to the negative third.
Okay, now can I solve for the change in B?
Well, how do you think you're gonna do it?
I'm gonna multiply those two.
No, not quite. Because then you'll end up with a velocity.
Yeah, I don't know what you want, but I was just gonna start there.
How? Let's sound the problem out. How far, not a velocity.
Do you wanna do the change in X?
Yes, so what kinematic do you think we want to use?
Probably 3 because we don't have a velocity final.
Right, see, we don't have a final velocity. What we do have is an, let's see, an initial velocity, which is what? It's 0. Because what you want to look for, starting from rest. That is a 0 initial velocity. If you see starting from rest, you should automatically cheer because one of your terms is going to disappear entirely. Okay.
Give me a try to do solve this one. Just don't look
So
up.
in this case, the theorems you start with are the kinematic equations themselves. And then that whole term becomes 0 because the initial velocity is 0.
Yes.
Why would you crash out?
Okay. Here's 1/2. 3.60. This is versus squared. What do we get?
Point 0288.
Yep. You can always leave your answers as that. You can call it 2.8 centimeters.
28.8.
Yeah, how fast will it be moving at this time?
Can I do my velocity now?
You just divide it.
Technically, yes, but
Yes, let's do it size this way.
Yeah.
But could I use the first equation?
So hold on.
so the first equation, well, yeah, you could, because your delta V is V final minus V initial, your V initial 0.
So could you do the first?
So V final.
I should do the first equation.
That's what I was saying.
So,
First one?
I would agree.
Thank you. I should petition for president. Yes. Oh,
I'd vote for you.
thank
I'd
you.
vote for you.
yes, you can also take the meters. Let's try to use the kinematic equation. Let's not use, like, we do physics in here. We don't use common sense, okay?
I swear, half the homework is
I'm gonna do homework twice and it's gonna be most common sense and it's gonna be only half a page. It's 12 pages.
Delta T is 1. What do you get?
What number? I think it'd be.
I should get the same answer as if I divided like that x by the time, right?
No, let's see.
One 44 question mark.
Why is there so many questions?
If you did it this way, what'd you get?
144.
Well, that'll go away if you keep working.
I got 144.
Me too.
There we go.
Okay, so here's my question. Should I get that same answer if I did change an x divided by changing two?
Theoretically, but,
Because I did not.
well, let's keep working with kinematic equations and see if we can't figure this out. That is not the first time you said that. You know, you're still holding on to your opinions from freshman year, that's what I was saying. Okay, so this is a more classic example. Two spaceships starting at the same starting point, moving in the positive x direction with constant accelerations. Spaceship 1 starts with an initial velocity of 2.0 kilometers per second and has an acceleration of 0.4 kilometers per second squared. Are you like doing Google Translate on something?
No.
Well, yes, that wasn't supposed to say something out loud, was it?
Do they have a translation for physics to English?
Did the little bird get mad at you or something?
Yes,
Had a tear on its eye.
I'm learning French.
Number one fear, the
Go
Duolingo bird.
talk to, go talk to that. Yeah, he speaks like 4 or 5 languages. He grew up in Morocco, so he speaks French, he speaks, their native language is called Berber, he speaks Arabic. Yeah. So the spaceship 2 starts with a velocity of 6 kilometers per second and has an acceleration of a minus 0.4 kilometers per second squared. So one I'm getting faster, one I'm getting slower. Find the time at which the spaceship 1 overtakes spaceship 2. Okay? What can you say about when one ship overtakes the other?
One's going faster.
Right, well, they're X final.
X fine.
They will overtake each other when they're in the exact same position. And that is the point at which they overtake each other. No, that's just letting you, this is when, so let's look at how that will actually fit in, okay? So, spaceship 1. Okay, for spaceship 2.
Is that a P? Or what is this?
Yeah.
What?
Is that
I think it's a one.
P-I.
No, it's a 1.
Starting
One.
Oh, an X. Oh, X1. Spelling bee.
Too fast.
Okay, so I have, from the kinematic equation, I have expressions for the final positions of spaceship one and spaceship two. Yeah, we're gonna have to set them equal to each other. And it says at what time, so you're gonna set them equal to each other, and you're gonna have to solve for delta t.
I sure will.
I feel like you're not gonna do it. Like, that was so sarcastic. You're like, yeah, I'm gonna do that.
Yeah.
Okay, so when we set this equal to each other. Oh, no. Then you have to solve for delta t.
So. I want to put numbers in before I rearrange.
Yeah, I don't want you to do that.
This isn't clicking my brain this way.
Why?
Because I told you, it's not about getting it perfect, it's about trying. If you try and you don't get it perfect, I can put comments down and say, do this or this or this. But if you just get lazy and you start putting numbers in at this point, you're just gonna lose your points.
But I would get the right answer, isn't it?
Okay, so you'll get 1 point out of the 4.
If I don't get the right answer, I'll still do what you're gonna do.
Oh
my. Do we have to do like what we do on the homework on the test?
Yes.
We have to put this side to that side. Well, I just didn't make it, you said it
Show
equals
me
zero.
all your work. So, what's the first thing we can get rid of? Yeah, those can become 0. Why?
Because the initial.
Yeah, because we're picking the starting position.
And I pick it to start at 0.
So we're setting 0 at where we start measuring the shifts, so it's just, it's kind of it's a selection. We can pick to put 0 there. So then I put the t squareds and the t's together. So let's see, what does that look like? No. Okay. Now, over here, I can pull out 1/2 t squared. Over here, I can pull out delta t. Okay. Now, the first thing I can do is I can divide through by delta t, get rid of that one, get rid of one of those. So then, we can have 1/2 t.
Divide both halves by delta t.
Then C is going to equal 2. So that's where we get to. If you look in the textbook, that's where he gets to. So this is where you start writing in numbers.
It's the same thing. There's a line.
Like you're traumatized.
My mom wants me to call this.
So what are we going to have? So your delta T is equal to. Yep. Once you derive for the, yeah.
So that was supposed to sound
Do I have to say it in French? But once we get to the point where you solve for the variable that you're trying to find, then you start writing the numbers.
Velocity 2. Minus the velocity
Wait.
over.
No, that's kilometers per second squared, isn't it?
So acceleration.
And you get a delta T of 10 seconds. You could, but sometimes I've had an app before where I just put the plus in there. I think everyone in here would get it, but I've had people raise their hands, well, where'd the plus come from? So I'm like, let's just show every step.
I am not sure.
Yeah, you can do that. This semester, you'll either get it or you'll be insane. What is it?
That was part A.
That was part A.
Not me.
In all fairness, you're not insane because of physics. You're insane because you chose to do a veterinary degree in 3 years.
You get called on that every day.
Yeah, because you've been doing what, like 18 credit hours a semester the whole time?
Fairness, 18 credit hours is not that hard to manage if you're good at time management.
Depends on the classes you're taking too.
That's true.
What's like
That's
these
probably-
classes? Oh, you're
When does
good.
2 spaceships have the same mass?
Okay, so we'll finish this one, finish this problem on Friday and continue on with the kinematic equations. I would really get used to the kinematic equations, taking the proper ones. Solving them because you're going to use a lot.
Is this gonna be on the test?
No. No.
So for the test.
Are you gonna give us homework 3 back?
The what?
The third homework?
The answers are online.
Study the in chapter exam.
So it's a high probability that